So we just started talking about complex variables. Something is very somehow something has been changed with I think I should have a choice of stroke. No, it's not. Okay. I thought it used to be a bit thinner. So z x plus I y. I sine theta. R. And I sine theta is called Euler's formula. And exponential minus I theta is cosine minus theta plus I sine minus theta is cosine theta minus I sine theta. So if we add them together, exponential I theta plus exponential minus I theta is cosine theta plus I sine theta cosine theta minus I sine theta. So naturally they cancel each other. It's twice over cosine theta. So cosine theta can be written as 1 over 2 exponential I theta minus I theta. Switch to mirror. I'm afraid if I turn off the mirror, then the screen will go off somehow. So, on the other hand, exponential I theta minus exponential minus I theta cosine theta plus I sine theta minus I no y cosine theta minus I sine theta. So this is cosine theta plus I sine theta minus cosine theta plus I sine theta. So this two those two cancel each other. We have 2I sine theta. So naturally, sine theta is, you divide by 2I, exponential I theta minus exponential minus I theta. So from Euler's formula, cosine theta is 1/2 exponential I theta plus exponential minus I theta. Sine theta is 1/2I exponential I theta minus exponential minus I theta. And without proof, we would like to extend theta to the complex domain. And assume that Euler's formula is always true. So when you are I think in middle school, you learned about 5 types of English sentence, type 1, 2, 3, 4, 5, right? Type 1 is, I go. I am a boy, right? Whatever. But maybe I shouldn't do that. I was going to sidetrack something. So, say if theta, if complex numbers, set theta is I times theta, Greek alphabet, then cosine I theta exponential I theta plus exponential minus I theta. Oops. Exponential minus I theta. This is called theta. Exponential I is minus theta, right? Plus exponential theta. And this function is also familiar to you. This is cosine hyperbolic theta, right? So, in complex domain, cosine I theta is cosine hyperbolic theta. So you can actually define complex angle. sine I theta over 2I exponential I theta minus exponential minus I theta. So that is 2I minus theta minus theta. The same as I times 2I minus theta minus theta. This is minus 1. So this is I over 2 exponential theta minus theta. And this is I sine hyperbolic theta. So another interesting result is sine I theta is I sine hyperbolic theta. Then when z is x plus iy, cosine z is 1/2 exponential iz minus iz. Because we assume that Euler's formula is always true, whether the argument is real or complex. Ix plus iy minus ix plus iy ix minus y minus ix plus y. So you can put exponential ix is cosine x I sine x exponential minus y 1/2 cosine x minus I sine x exponential y. So let's put cosine x together. Then 1/2 we have minus y plus exponential y. On the other hand, if we put I sine x together, we have exponential minus y minus exponential y. And this is cosine hyperbolic y, right? This is minus sine hyperbolic y. So we have cosine x cosine hyperbolic y minus I sine x sine hyperbolic y. And actually, we can also check whether the trigonometric addition theorem same, right? On the other hand, you probably remember this, right? You probably had learned this addition rule or theorem in your freshman high school or maybe senior middle school, either way. So let's try to apply whether this is also true for the complex number. So cosine x plus iy. So if you apply this, cosine x, cosine iy, sine x, sine iy. And we just have learned that cosine iy is cosine hyperbolic y. Cosine x, cosine hyperbolic y, minus sine x. And sine iy is nothing but I sine hyperbolic y. So let's compare the previous result with this. So we can actually use this. So that means we can use addition theorem. So sine z is sine x plus iy, sine x cosine iy, cosine x sine iy, sine x cosine hyperbolic y, plus I cosine x sine hyperbolic y. Up to now it's okay. Tangent g. Cosine z over sine z. Right? Cosine x cosine hyperbolic y minus I sine x sine hyperbolic y, right? Sine x cosine hyperbolic y, I cosine x sine hyperbolic y. I need to check this. Looks complicated, right? So when you have a complicated situation, what do? Just do nothing, or multiply by 1. Cosine x hyperbolic y, I sine x, hyperbolic y, cosine x, y plus I sine x, sine hyperbolic y. It looks a bit complicated, so for now let's just put this way, dz and z. It's called denominator. So in Korean, denominator is 분자, and nominator is no. Nominator is 분자, denominator is 분모. So let's calculate separately. So dz So all you need is a patience. So this is actually complex conjugate, so you know the result, right? Cosine square x, cosine square y, plus sine square x, sine hyperbolic square y. And you can use this 1 minus cosine square x, cosine square x, cosine hyperbolic square y, plus 1 minus cosine square x, sine square y, hyper square y. So cosine square x y minus hyper square y, hyper square y. Anybody remember this? Cosine hyperbolic square minus sine hyperbolic square is always 1. Same as cosine x square plus sine x square is always 1, right? And so this is cosine square x, sine hyperbolic square y. If you're not sure, you can check. Let me say four times exponential x square minus 4 times exponential x square, 4 times 2x plus 2 minus 2x minus 4 times 2x minus 2, 2x. So this cancels with this, 1. Denominator, so we obtain denominator is cosine square x sine hyperbolic square y. Denominator sine x cosine hyperbolic y plus I cosine x sine hyperbolic y cosine x cosine hyperbolic y minus I sine x hyperbolic y. So I don't have a pointer, so you just have to follow me. Sine x cosine hyperbolic y. So we multiply the first component together. Cosine x cosine hyperbolic square y plus, we put the imaginary parts together, then they become plus cosine x sine x. Oh, this is plus, right? This is minus sine hyperbolic square y plus I cosine square x sine square y cosine square y plus I sine square x cosine square y sine hyper square y. So this is cosine x square. No. Cosine x sine x cosine hyperbolic square y minus sine hyperbolic square y plus I cosine square x plus sine square x sine hyperbolic y cosine hyperbolic square y. So this is 1, this is 1. So it becomes cosine x sine x plus I cosine hyperbolic y sine hyperbolic y. Let me check if my answer is same. Yes. So tangent to z be complicated. Cosine square x sine hyperbolic square y sine x cosine x I sine hy cosine hyperbolic y. So it would be interesting to do this as a homework. I would say secant z is 1 over cosine z, CSG cosecant z is 1 over sine z, and cotangent z is 1 over tangent z. So you can do the same thing as what I have done in my class. So express this is a function of x and y. Now cosine hyperbolic c. Two over exponential z minus c x plus iy minus x minus iy 1/2 exponential x cosine y plus I sine y plus 1/2 exponential minus ix cosine y minus I sine y 1/2 exponential x plus exponential minus x cosine y plus I 1/2 sine y is cosine hyperbolic x cosine y plus I sine hyperbolic x sine y. Oops, you cannot see them well, right? It's time to copy this. Oops, I gave you homework, some homework too. All right, 1, 2, 3. Sine hyperbolic c 1/2 exponential c minus c, right? So 1/2 exponential x plus iy minus 1/2 exponential minus x minus iy. So 1/2 exponential x cosine y plus I sine y minus 1/2 exponential minus x cosine y minus I sine y. So if you put them together, cosine y 1/2 exponential x minus exponential minus x cosine y plus I/2 exponential x, and so we have minus minus, right? So plus exponential minus x sine y. So this is cosine hyperbolic x cosine y. Oops, sorry about that. Sine sine hyperbolic y plus I cosine hyperbolic y sine y. So I'll give you homework as a tangent hyperbolic c, secant hyperbolic c, cosecant hyperbolic c, cotangent hyperbolic c as a homework 2. So I have how many? 1, 2, 3, 4, 7, 4. So you have 7 homework. So I think each function will take about 5 to 10 minutes, so it will take about 1 hour. So if you have nothing to do for 1 hour, then it's perfect time to do homework. And the best opportunity for you to do homework is some of you on a blind date and your partner didn't show up. So you decide to wait 1 hour. So what you can do is you do this homework. So for 7 problems, you can spend like 60 minutes, and still your partner didn't show up, you just go home, right? So do homework when you are stood up. That's the expression. On a blind date or something like that. Blind date is 소개팅, and your partner didn't show up, but you decide to wait 1 hour. So what do? Do homework. And the benefit of doing homework during while you're stood up is you will get a good grade as a benefit too, right? So. Why don't you take a break for 5 minutes and continue? So as I told you, homework is you just do at home. Don't bother to turn in. Polynomials. Say z x plus iy z to the second square x plus iy x plus iy x square plus iyx ixy minus y square x square minus y square plus 2iyx. So you can define the polynomial of z, or z to the power. Z to the cube is z squared times z x squared minus y squared plus 2ixy x plus iy. So x squared x cubed minus xy squared plus 2i x squared y plus I x squared y minus iy cubed
plus I cube minus 2xy square. So x cube minus 3xy square plus I 3x square y plus y cube. So you can define similar way. So maybe just two more homework. Z 4 z to the 5 homework. So there's 9 homework problems. So far, all the functions have been behaved very nicely. So far, we have single-valued functions. Single-valued functions, you put z, you get fg out, just one value. So it's like a coffee machine. You put coin, you get coffee out, right? So one coin for one coffee. You never get 2 coffees out, right? That will be nice. If you put one coin, you get 2 coffees out. That would be awesome. Fantastic, right? So one coin, one coffee out. Just single-valued function. But there are other functions. Say, you like square root of z. Exponential 2 pi I, remember that? Is cosine 2 pi plus I sine 2 pi, right? Which is 1. How about exponential pi I? Cosine pi, I sine pi, right? Cosine pi is minus 1. So when you take a square root, you can multiply always by 1, right? But if you take a square root or rational power, but this is minus 1, right? So let's define square root of z when z is real positive. Then z is square root of z plus minus 1, depending on the argument, because minus, plus, minus. So this is the case when you put one coin, you have two coffees out. So normally we define some cut. This is called branch cut, such that theta takes 0 to 2 pi. So when you take a theta, it never crosses the x-axis. If you want to make a function single valued, then you have to use the branch cut. So to make a in order to define one needs a branch cut confining theta to theta to 2 pi or etc.
So you have to be careful when you want to define the multivalued function.
So, for example, I want to solve this problem. Then z 1/2 exponential I n 2 pi and can be 0, 1, 2, etc. plus minus 1. If you want to solve this, t cubed to the 1 is exponential plus minus 2n pi I. So n is integer, n is 0, 1, 2, etc., etc. Then z is exponential plus minus 2n pi I 1/3. So you have three different solutions. One is z can be 1 plus 3/2 pi I 2 pi I. So you have three different solutions here. 1, 2, 3. C1, C2, C3.
So if you have a rational power of a rational number, you have to always worry about the function may be multivalued. Another function is logarithmic. Yes?
How can you have a function that's multi-valued?
Because, you can always multiply by 1. But 1 can be represented by Euler's formula, 2 pi I minus 2 pi I, etc., etc. And then if you take the power of like a rational number, then
say if we have 2 pi I, which is basically 1, right? You have minus 2 pi I, which is also basically 1. But if you have take a power of 1/3, then what do you get? 2 pi I to the 1/3 exponential 3 over 2 pi I, right? That is cosine 2 pi over 3, I sine 2 pi over 3. So that is cosine 2 pi over 3 minus 1/2, I think. Square root of 3 over 2, right? Cosine pi over 3 is 1/2, right? Sine pi over 3 is square root of 3 over 2. On the other hand, if you take minus 2 pi I over 1/3, you get cosine 2 pi over 3 minus I sine 2 pi over 3 is minus 1/2 minus I root square root over 2. When also exponential I 0, if we take a 1/3, this is 1 too, right? This is basically 1. So you have 3 different powers. And of course you can increase to the 4 pi, still get the same answer. So if you take the power of 1/3, you always get 3 different roots in complex domain. Another interesting thing is you can represent polar representation, but also you can say 2n pi, because this is 1, right? So you can always multiply by 1. But the thing is, if you take the log z is log r exponential I theta plus minus I 2n pi log r plus minus I theta, I theta plus minus 2n pi. So again, you have a multivalued function. So this gives you multivalued. So you need to confine which angle you want to use. So especially you like to confine your angle from 0 to 2 pi. Otherwise you have angle can keep multiplying and you have a different imaginary numbers. So when we confine theta to 2 pi, we say ln z as a big ln z. So limit to single valued z. Value the function. So even though you can define the log functions and fractional power of a polynomial, then you have to worry about multivalued properties of a function. So fractional power of C, logarithmic function. And inverse cosine, inverse trigonometry or hyperbolic function.
In this case, also, you have to worry about the multivalued properties.
For example, let's say W is cosine inverse function.
Or arc cosine. Sometimes you use arc cosine.
This means cosine W is C, right? Is exponential IW minus IW 2Z, same as exponential IW plus 1 over exponential IW. You can multiply exponential IW on both sides. Square plus 1 is 2Z exponential IW. So exponential IW square minus 2Z exponent IW plus 1 is equal to 0. Whew. Exponential IW can be solved. C plus minus C square minus 1 square root of 1 over C plus 1/2. So when you say this form is for single valued, so you can either put plus, minus, or just 1/2. Then IW is log ln Z plus Z square minus 1/2. W is minus I ln C.
So for this function, this part, fractional power is multivalued, right? And log is also multivalued. So basically, this arc cosine function is multivalued function.
I'll give you some more homework. Sine inverse C, cosine hyper inverse C. More homework.
So far, we have defined the complex functions. So if you trace back your school
days, you started learning polynomial functions in middle school, right? You first learned the variable x, and then x squared, something like that. And maybe toward the end of the middle school, you learned about cosine, sine. And if you get into high school, probably you have learned exponential function, log functions, etc., hyperbolic functions. So you first learned about functions, to define functions. And after that, what did you learn? Calculus, differentiation, and integration. So now we are going to turning our attention into differentiation, complex. So differentiation of functions. There are several prerequisites. What is that? If you want to take a derivative of function fx, so what is the condition for that particular function? It has to be
Single value.
single valued, of course, and continuous. Continuous, right? So say this is x, this is y. You call this domain. The region that your function is defined, and you call D. Say you have a C at some point C and near point C naught. This continuous means when Z minus C naught is some smaller than delta, then Fc minus Fc naught is smaller than epsilon for very small delta and epsilon both greater than 0. So some very tiny minute number delta, and if your two complex points is the distance between the complex points is less than delta, then the difference of the function is less than epsilon. Then we say that particular function is continuous. Then if we can define when this result is unique. If this limit is unique, then we can define the complex derivative. So two things are needed. One is the function itself has to be continuous, and this particular limit has to be unique. If there is a unique limit exists, then you can say the function is differentiable. So if Fc is continuous and above limit, say this limit, say star is unique, then Fc is differentiable. In real variable, we only need the requirement is continuous, right? But actually also require uniqueness, because you want to have a left limit or right limit is same, right? So that is uniqueness. So if this limit is unique and its function itself is continuous, then we say that this function is differentiable. And we are going to do a little bit more explicitly about the differentiability. So this part is a bit abstract. Say f c, we can define real part and imaginary part of function. And delta z, delta x plus I delta y, of course. So let's calculate this limit first. I free xy. So let's consider the two cases. One is the case 1. Delta x is set to 0. Okay, that's the other way around. Delta y is set to 0 and delta x going to 0. In that case, delta y is 0, right? So we have delta x u x y free y minus u x free x y. So when delta z goes to 0, delta z f x plus delta z minus fz is basically partial x u x plus delta x y minus u x y delta x I free x plus delta x y free x y is partial x partial u plus I partial x partial v. Case 2 is you like to compare this. Case 2 is partial x partial y. Delta x is equal to 0, delta y is going to 0. Then delta z f z plus delta z minus fz is I delta y, right? U x y plus delta y plus I free xy plus delta y minus u xy minus I free delta y xy, right? So this is I delta y u xy plus delta y minus u. Oh, I think this is wrong. uxy plus I delta y I free xy plus delta y minus free xy, right? So this is basically minus I partial y partial u plus partial y partial v. So two limits must be unique. For uniqueness, the previous result, two limits must be the same. So partial x partial u plus I partial x partial v is partial y partial v minus I partial y partial u. So that means we have condition partial x partial u must be same as partial y partial v, and partial x partial v is minus partial y partial u. This is very important condition for the function to be differentiable, and it has a particular name, Cauchy-Riemann condition. Or CL. Then defined as partial x partial u partial x partial v. If the Cauchy-Riemann condition is satisfied, then we can define this partial derivative. So we can guess the core of next quiz will be checking this condition for given function and then find the derivative. That's good quiz problems, right? So I'll give a hint for next quiz problem. So the second condition for the Cauchy-Riemann condition is partial v partial x must be minus over partial u partial y. So for the second quiz, I think half of the problem is about this Cauchy-Riemann thing and finding derivative.
looks can be deceiving. Looks very easy, right? How about tangent z? Say, so this plausible quiz problems. Check Cauchy-Riemann condition for fz and find dz dfg. Would be a very good quiz problem. Say fg is easiest case, d square. Whether this function is differentiable or not. X squared minus y squared plus 2ixy, right? So in this case, uxy, x squared minus y squared, 3xy, 2xy, right? So Cauchy-Riemann condition, you have to memorize this. Partial x, partial u is 2x. Partial y, partial v, 2x, right? So partial x, partial u is partial y, partial v. So we have one condition satisfies. How about partial y, partial u? Minus 2y, right? Partial x, partial v, 2y. So partial y, partial u is minus partial x, partial v. This is second Cauchy-Riemann condition, right? If we go back to the... So one thing is it's differentiable, right? Differentiable. So, but goal is to find the derivative. So dz, dfc is partial x, partial u plus I, partial x, partial v. I mean, you have to follow. So 2x, 2y, twice of x plus iy, 2z. So when you so actually you obtained the basic derivative of a real function. If you take a derivative of x squared, you get 2x, right? Same as if you have a z squared, then you have 2z. But things can be very complicated, right? So as a preview, maybe I can give you fc z to the 5. It's non-trivial if you want to calculate the real part, the imaginary part. It may take 5 minutes. So fc uxy ivxy. So find u and v. Check CR condition satisfied. Show that five to the d fourth. So that can be a good quiz problem, for example. So maybe you want to do it as a homework as well. This is a good exercise for you. Another good exercise, if we have a complex conjugate. This function is not differentiable. So u is x, v is minus y, right? So partial x, u is 1, partial y, partial v is minus 1. So partial x, partial u is not same as partial y, partial v. So that means Cauchy-Riemann condition is not satisfied. So not differentiable. Maybe just one more example, and I will let you have your lunch. Say FC and two more examples. Say, I'm sorry. Simple thing, cosine z. This is easy, right? Cosine x, cosine hyperbolic y, sine x, sine hyperbolic y, right? So uxy, I vxy. So uxy, cosine x, cosine hyperbolic y, vxy, sine x minus sine hyperbolic y. Partial x, partial u. If you differentiate the cosine x, you get minus sine x, right? Cosine hyperbolic y. Partial y, partial vxy is minus sine x. And if you differentiate sine hyperbolic y, what do you get? Cosine hyperbolic, right? So the first relationship is true. Partial x, partial u is partial y, partial v. Partial y, partial u is cosine x. If you take a derivative of cosine hyperbolic y, you get sine hyperbolic, right? Sine hyperbolic y. Partial x, partial v. You have minus, take the derivative of sine x is cosine x. And sine hyperbolic y. So partial y, partial u is minus of partial x, partial v, right? So we have two conditions satisfied. Cauchy-Riemann condition is
satisfied. Say Riemann is, I think, 1m or Riemann 2m. Oops. Let me check whether sometimes I'm confusing. One M or sometimes Riemann. Riemann. Yes, 2n is correct. So my memory is correct. So differentiable. So dz dfc is partial x partial u plus I partial x partial v is minus sine x cosine hyperbolic y minus I cosine x sine hyperbolic y. It's basically minus sine z, right? What about sequent to z? 1 over cosine z.
Would be a bit messy, right?
So let me check. Cosine x cosine hyperbolic y plus I minus I sine x sine hyperbolic y 1 is cosine x cosine hyperbolic y plus I sine x y cosine square x cosine hyperbolic square y plus sine square x sine hyperbolic square y is, I think we have done this. You can reduce cosine square x sine hyperbolic square y cosine x y sine x sine hyperbolic y. So u xy is basically cosine square x sine square y cosine x cosine hyperbolic square y, right? And 3xy is sine x y hyperbolic square y.
Oh, now it's a bit complicated because we have functions in the numerator and denominator.
So partial x
What do you do?
y, and this, right?
The first part is easy.
First part is simply cosine square x plus sine hyperbolic square y minus sine x cosine hyperbolic y. On the other hand, this is, you need to square this first. Square, and you have minus sine, and then you differentiate this. 2 sine hyperbolic square y square y, right?
You have checked. So 1 over this denominator, you square it, and you put minus sign, and then you take derivatives. So chain rule, right? So we learned about chain rule in vector analysis.
So let me just put down the result. So put together y square minus sine x cosine hyperbolic y cosine square x plus sine hyperbolic square y square minus, oh, minus this is partial x. Sorry about that. So I did everything wrong. Minus twice over cosine x sine x, right? So minus minus plus cosine square x sine x cosine hyperbolic y so it becomes cosine square x plus sine hyperbolic square y. Oh. There's no. So minus sine x cosine square x cosine hyperbolic y minus sine x cosine hyperbolic y sine hyperbolic square y 2 cosine square x sine x cosine hyperbolic y. So we put together, what do we get? Cosine square x plus sine hyperbolic square y square 1 cosine square x sine x cosine hyperbolic y minus sine x cosine hyperbolic y sine hyperbolic y. So we can put together denominator is cosine square x plus sine hyperbolic square y square and sine x cosine hyperbolic y cosine square x minus sine hyperbolic square y. Say v cosine square x plus sine hyperbolic square y. I'm laughing, but
You don't have to laugh. The same thing, partial y.
maybe I should use small letter. Cosine square x square y. If we take a derivative of y, sine x cosine hyperbolic y, right? Minus now derivative of denominator cosine square x plus sine hyperbolic square y square and sine x y twice over sine hyperbolic y cosine hyperbolic y, right? So same as before, cosine square x sine hyperbolic square y square sine x cosine hyperbolic y cosine square x square y minus twice over sine x sine hyperbolic square y and cosine hyperbolic square y. Cosine square x sine hyperbolic square y square, we have a cosine square x sine x cosine hyperbolic y plus sine x cosine hyperbolic y sine hyperbolic square y minus twice over sine x sine hyperbolic square y cosine x is cosine square x plus sine hyperbolic square y and This is cosine square x sine hyperbolic x cosine hyperbolic y minus sine x sine hyperbolic square y cosine hyperbolic y. This is sine y, right? So sine, we can put sine x something is sine x sine cosine I think this is sine x cosine hyperbolic y and cosine square x, right? So I think I made some mistake. Sine x cosine hyperbolic y. So sine x cosine hyperbolic. Oh. So I'm getting snobby. So sine x cosine hyperbolic y cosine square x plus sine x cosine hyperbolic y, right? So cosine square x plus sine hyperbolic square y square sine x I think I'm keep having mistake. This must be sine x cosine hy, right? And cosine square. Oh. Cosine square x minus we have sine square y, right? Wow. So this is same as partial x partial u.
It's half of the story. The other half of the story is just be patient. I think I should try to slow down because I don't know. I still need the coffee to wake me up. Now let's go back. For next slide. This right. Square, cosine, cosine. To u. Cosine x, cosine hyperbolic y, cosine square x, sine hyperbolic square y, right? Now partial y, partial u. So we first take the derivative of y in the denominator. So cosine hyperbolic y become sine hyperbolic y, right?
So cosine x sine hyperbolic y, cosine square x sine hyperbolic square y, and minus cosine x cosine hyperbolic y, this is square. And then take a derivative. So twice over sine hyperbolic y cosine hyperbolic y, right? So I think we are getting faster. Cosine square x sine hyperbolic square y square cosine x sine hyperbolic y cosine square x sine hyperbolic square y minus twice cosine x cosine hyperbolic square y sine hyperbolic square y cosine square x sine hyperbolic square y square cosine three cube sine hyperbolic y cosine x sine hyperbolic square y minus twice cosine x cosine hyperbolic square y sine hyperbolic square y. So this factoring. So cosine x sine hyperbolic y, then you put cosine square x minus cosine hyperbolic square y and cosine x sine hyperbolic y. You have this is square. A cube sine hyperbolic square y minus cosine hyperbolic square y. So it becomes minus 1. Cosine square x plus sine hyperbolic square y square cosine x sine hyperbolic square y. We have cosine square x minus sine. This is a cosine. Cosine hyperbolic square y minus 1. So cosine square x minus 1 is minus sine x, right? So it becomes minus cosine square x plus sine hyper square cosine x sine hyperbolic square y sine square x plus cosine hyper square y. Just one more thing, right? So we have covered 3 out of 4. So you are following the calculations? Just you need to have a patience. Just one more, and we all set. Voila. Same as this with a minus sign, right? So, free. Free sine x sine hyperbolic y cosine square x sine hyperbolic square y. Partial x partial free. So we take the denominator first. So cosine x sine hyperbolic y cosine square x sine hyperbolic square y minus sine x square y square sine hyperbolic square y square. If you have a cosine, you have minus, right? Minus twice of cosine x sine x. So we have basically cosine square x plus sine hyperbolic square y square cosine x sine hyperbolic y cosine square x sine hyperbolic square y plus twice over sine square x cosine x and sine hyper square sine hyper y, not square. So cosine square x plus sine hyper square y and square and sine x cosine x sine hyperbolic y. You have cosine square x plus sine square x. This is square, right? Plus cosine x sine hyperbolic y sine hyperbolic square y plus sine square x. And this is 1. So we have cosine square x plus sine square hyper square x plus cosine x sine hyperbolic y 1 plus sine square x plus sine square y. And sine square y is actually cosine square y minus sine square y is 1. So this is cosine hyper square y minus 1, right, basically. So we can write it down as cosine square x plus sine hyperbolic square y cosine x sine hyper y sine square x plus cosine square y. I hope I didn't make any mistake this time. And let's compare. So this is minus partial y partial u. Wow. So patience paid off. So we have cos Riemann condition satisfied.
So that means sequence Z is differentiable. That's half of the story, right? So actually we need to find the derivative.
Few slides. I still haven't figured out how to make a copy. So dz dfz is partial x partial u plus I partial x partial v. So where was it? Partial x partial u was, let's go back. This is cosine square x plus sine hyperbolic square y, and we have a square or no? Let me see. Partial x. We have a square sine x cosine hyperbolic y cosine square x minus sine hyperbolic square y plus I cosine square x sine square y square cosine x sine hyperbolic y sine square x plus cosine hyperbolic y. And you can actually simplify. Perhaps I can give this part as homework. I think it will take another half hour, maybe 30 minutes to show this, but actually you can do this at home. Because we already have a tangent to Z, right? Somewhere along in my class, tangent to Z, cosine Z, tangent to Z. Right, tangent to Z. Cosine square x, sine hyperbolic square y, sine x, cosine x, I sine hy, cosine h.
Maybe I can do this, or maybe you can do it at home.
So square is easy, so you just show this and use this and put it back here, and then let's do this homework.
And probably I'd like to stop here today and next week.
How about that?